Alrighty, now for something slightly different. As you can see by the picture, we are done with energy, and we are back on Newton. Now we're going to start talking about impulse and a different quantity called momentum. Momentum, kind of like energy, there's no new physics really being done here in this next chapter. This momentum, similar to energy, is just a different way to view a system or analyze motion that is occurring in a system. It's a new perspective on how you can relate forces to motion. We saw with Newton's laws, for example. Newton's laws, you can use Newton's laws to find the instantaneous acceleration on an object. What is at that very instant in time? How is the object accelerating? How is its velocity changing? Which allowed us to solve some interesting problems. But nonetheless, I think had the unfortunate requirement that we're always thinking about accelerations. And my intuition is much more akin to thinking about velocities. I can visualize things moving in different directions and maybe speeding up and slowing down a little bit, but when I'm thinking about instantaneous accelerations and somehow connecting that to an object, it's a little bit harder for my mind to wrap around acceleration than velocity. Energy provided some help in that regard. We looked at energy where we could define this quantity that depended on velocity, the kinetic energy, 1/2 mv squared, and we saw that the reason that kinetic energy changed was because of work being done on the object, which of course is from forces. None of this is saying Newton's laws were wrong, but energy just used forces and looked at the system in a slightly different way, rather than looking at instantaneous accelerations from contact forces or a long-range gravitational force. It looked at how forces were being applied over distances. If the object was moving, and a force was acting on that object while it was already moving, then this thing called kinetic energy could increase or decrease based on whether there was positive or negative work being done on the system. And if we were able to restrict ourselves to systems where in that system only conservative forces were doing work, then the total energy of that system remained a fixed constant with time. Which proves very useful and very helpful. Because if something is constant as a function of time, we can connect to incredibly distant moments just by saying that their total energy must be overall conserved. And this is an example of just an overall experimental fact that appears to be the case, of that energy is always conserved as long as you take into account what forms of the energy is in. So even in the case where it's not just kinetic and potential, you could have something like friction that is slowly taking energy away. That energy nonetheless then is becoming something else that exists outside the system. Thermal energy, heat, for example, or light could be turned into light as a possibility. So we could say that energy conservation says that the total energy of the entire universe is a constant. But when we're looking at smaller systems where we only are dealing with smaller systems where only conservative forces are acting, then we can say the total energy is also constant in those cases too. Because it really doesn't have to be that small. The Earth going around the sun. If you just look at the motion of the Earth and the sun as they orbit around, it is just gravity that is pulling on both of those objects, which is a conservative force. Energy is still conserved in the solar system, for example, if you look at the motion of the planets and the sun. So I guess small is subjective. We're now going back a little bit and talking about momentum, which is getting us back into talking about forces. But again, we're going to look at how forces are applied to objects in a system in a slightly different way, rather than looking at the instantaneous moments, where instead of looking at forces over distance, momentum is all about looking at how forces are applied over time. So if an object exerts a force over some amount of time, that can change this quantity that we will define as momentum. This can be very, very useful for looking at, say, collisions. In a collision, there is a abrupt and usually very large contact force that exists between the two objects. Taking a ball and bouncing it on the table. When it bounces off the table, it is in contact with the table for a very short amount of time, but the table exerts an incredibly large contact force on the ball, which allows the ball to fly into the air and then off into nowhere. Well, no more ball. But in these cases, it was the contact force with the floor, or with the table in that case, was incredibly large that gave so much acceleration to the ball, it was able to fly into the air. Looking at those sorts of things in terms of momentum can be very helpful. So to give a little bit of a similar summary of where we're going, we will find that momentum also has nice conservation properties if we are smart about how we define our system. We saw with kinetic energy, or with energy in general, if there was no non-conservative forces and there was no external work being done on the system, then the total energy of that system remained constant. Similarly, we will find for momentum, if there are no external forces acting on a system, which the system now in this case could be defined as having multiple objects, the table and the ball, in the case of a ball bouncing off a table. If I define my entire system as the table and the ball, then all of those interactions that occur between the table and the ball conserve this quantity that we're going to call momentum. The total momentum of table plus ball remains the same. And again, the big, I think, utility that comes from momentum arguments is in dealing with collisions. To give an example of a ball being thrown against a wall, which I would demonstrate if I had not just lost the ball. So you have a ball, and I suppose it's coming essentially horizontally towards the wall. When it is not in contact with the wall exerts no force on the ball. But there comes a point where the ball is in contact with the wall. And in that case, the wall, since it's touching the ball, there is a contact force. Turns out it is a quite large contact force from the wall. If you want to call it the normal force from the wall is quite enormous, because that force has to, in a very short amount of time, take the velocity of the ball, shrink it to zero, and then make the velocity of the ball, some non-zero value pointing in the other direction, where the ball then is moving, away from the wall in that case. So in order to create that delta V, that change in velocity, over a very short amount of time, recall, it's doing some delta V over a very short amount of time, that results in a large acceleration, which is the result of a large force. How to understand this with Newton's laws can be a little bit challenging, but with momentum, we'll see, is more straightforward. Let's ask a little ourselves first about how our intuition is about collisions and how we'll be able to answer these thinking about momentum. So assume that all of these take place on a frictionless table. A tennis ball rolls across a table and hits another tennis ball. If you were to imagine what that motion looked like, what the tennis ball is doing after the collision, what would you guess? Found the ball. So in the case of two similar balls rolling and hitting each other, now you might imagine, right, I could ask, in that case, if two similar balls roll, one rolls and hits the other ball, after the collision, are both balls moving? Is only one ball moving? Which directions are the balls moving in? Commit yourself to an answer. Then you could think, okay, what about case 2? A tennis ball rolls across the table and hits a bowling ball. After the collision, is the bowling ball moving? If so, what direction? Is the tennis ball moving? If so, what direction? Or some different cases. There's a cardboard box. I'm assuming it's a light cardboard box, and there's a clump of mud that's essentially about the same mass as the cardboard box. You throw the clump of mud at the cardboard box, and it sticks to the box. What happens to cardboard box plus mud after that collision occurs? Or similarly, you have a runaway semi-truck that collides into a small car. What is the motion of the semi-truck before and after the collision? What is the motion of the car before and after that collision? Some of these I have some immediate intuition for. Number 4, I would say the car then becomes, a decal on the front of the semi-truck, and the semi-truck just keeps going, essentially, in the forward direction. And the little car goes along for the ride. For a tennis ball rolling across the table and hitting a bowling ball, I might imagine that the bowling ball is not going to be moving that much, and the tennis ball will probably bounce backwards. But the ones that are a little bit harder is maybe 1 and 3, where they're about the same size and they hit each other. What's going on? And then when they're about the same mass and they hit, what's going on? And then for number 3, they're about the same mass, but they stick. What's going on? So we can demonstrate this using our air track. So the idea here is Professor Kittner is going to put one mass on the air track, and she's going to place another one that is either going to be the same mass or twice the mass. So in this case, we're looking at equal masses. And then she will send off one of them towards the other. They will collide. They are not allowed to stick to one another. And we can see what happens in their motion. So here's another air thing of equal mass. So in the case of equal mass, it appears like all of the forward movement gets sent to the other object it collided with. Go back a little bit. Right, thus the one in the back essentially comes to rest, and the other one moves forward at roughly the same speed that it was going at before. This is not a perfectly elastic collision. A little bit of energy seems to be getting lost. Interesting. And you can actually do that if you had two, I won't do this now on my table, but if I take 2 balls and I roll one across and they hits the other one, the one that was rolling first comes mostly to rest. Now here's the case where they are unequal masses, and I forget which hits what. So here's the more massive one. You can see there are kind of some silver weights on the top. All right, so that one's going to be stationary, and she's going to send the smaller one. So the lower mass one is going to be the one that she sends off to collide with the larger mass. So in this case, this might be, the tennis ball is thrown at the bowling ball. So we're going to flip them. All right. I don't want to flip them yet. All right, so you can imagine the bowling ball on the left, the tennis ball comes off on the right. In this case, both of them started to move. But in this case, the smaller mass one started to move in the opposite direction. And then even the more massive object started to move, but continued to move forward. All right, so then if we switch the order, so now the larger mass is being thrown at the smaller mass. It might be the semi-truck Well, I guess no, that's not sticking. You know, the bowling ball thrown at the tennis ball. Let's back up. So in that case, the more massive object hit the smaller object, but then they both still kept moving in the same direction. Where before, when the order was reversed, you know, the smaller object turned around and started moving in the opposite direction while the big object moved forward. When it was the opposite kind of collision, you know, they both kind of moved in the same direction. Which again, I guess you can kind of think of it like, you know, the semi-truck and the car, if they didn't stick to one another. Or an example of where now they're the same mass again, but now they're allowed to stick. So we've put a little piece of Velcro and felt on the ends of them, so they will stick together when they are thrown. So in this case, when they stick together, there was forward motion initially. And then after they stuck together, they then continued with that forward motion, but in this case, exactly half as fast. Then they started moving as essentially just one mass that now had doubled. And then same sort of situation, but now they are allowed to stick to one another. All right, so it looks like she's throwing the big one towards the light one. Okay, we can do it again. So they still were moving together in the same direction, but again, notice that the speed decreased. All right, we're going to try the opposite case now. Yes. Put the felt on the right side. Well done. The air track is not perfect, trying to keep things stationary. That one seemed to be more dramatic. In this case, the smaller guy came in, stuck to the big one, but then had a really hard time making them all move together as one. The speed took a very dramatic drop. Where in the reverse, the speed did get smaller, but not quite not quite as much. You know, it didn't drop down by a factor of 2, it dropped down less than a factor of 2. But in this case, it was definitely more than a factor of 2. So what's going on with all these cases? Thinking ahead that we're going to be thinking about some sort of quantity that quantifies this motion. There is some sort of forward motion that was associated with one of the objects, and that forward motion got transferred or transformed into different ways, depending on whether it was the massive object hitting the smaller one, whether they could stick or bounce off each other. There were different kinds of collisions operated somewhat differently. But I claim in all of these cases, this quantity called momentum, which you could think of it as kind of a moving inertia, maybe might be a way to call momentum, is conserved. You know, if you've ever been to a state fair or a carnival, and you've been on bumper cars, that's another great example of where momentum can be, a fun way to spend the evening. You know, when you're in a bumper car and you bounce off another car, what you're doing is you're exchanging your forward oomph with each other. You are moving with some velocity, but the collision will change your direction and it might change how fast you're moving. So what you're doing there is you're exchanging this thing called momentum. All right, so let's go back to this ball hitting the wall. That is a kind of a simple enough case that we can use kind of to motivate ourselves. If you were to analyze as a function of time, and this would be, again, a few milli is actually too large, like a ball bouncing off a wall, really it's in contact with the wall for a very short amount of time. It might be in the order of microseconds to tens of microseconds. And we're just looking at, say, the force of the wall on the ball. So if it was possible for us to measure, as the ball, came into the wall, hit the wall, turned around, and came back off the wall during that collision, that rebound. If you were to measure how much force, what is the magnitude of the surface force pushing back on the ball, what would it look like? Well, there's some point where it comes in contact with the wall. So I could call this point the point of contact. The point in time, really, of contact. The point in time, on whoever's measuring with a clock, of when the object comes in contact with the wall. And then similarly, there's a point of breaking, right, where ball loses contact with wall. In which case, there cannot be a surface force. That has to identically go to zero. If there's no contact between the objects, there can't be a contact force. And if you were to measure this, it would look something more kind of like a bell curve or a Gaussian. That might look something like this. It might not even necessarily be symmetric. Depends on the properties of the ball, the properties of the wall. But it would be something that, it starts at zero, quickly increases, as the normal force really pushes back on the ball. And then as the ball starts to lose contact with the wall, diminishes back down to zero. Right, this would be the wall force, but now it's a function of time. The ball is in contact with the wall for a given amount of time. At every instantaneous moment in time, there's a force pushing back on the ball. But that the total amount of force that is being pushed on, that the ball is being pushed on with, is constantly changing. We can see this. There's another movie here of just, even for objects that you might think as being quite rigid, like a golf ball, there's still some deformation, which kind of very much displays that there is a very, very large force being acted on the golf ball when it comes in contact with, in this case, it's going to be a golf club. So a golf club is going to come swinging apparently at different speeds. Or these, I guess, are the resulting speeds of the ball. But in all the cases, the point to take away here is that you see the golf ball does actually change shape in all of these cases. And then when the movie moves forward, the ball essentially pushes itself off of the golf club. I can go back to this. In all of these cases, you can see the deformation that occurs from the golf ball. A very large force. Try to squeeze a golf ball with your hand and change its shape like this. I reckon it'd be very hard for you to accomplish that at all. But there's an incredibly large force from the golf club smacking into the ball, and over a very tiny amount of time, again, microseconds, the golf ball, it feels a very large, incredibly large force, which then allows it to sail off. I think there's another one. Yeah, it just kind of, I guess, shows same idea here. Then you can see the ball will then eventually re-expand back out, and then it kind of works its way and flies ahead of the golf club into the air. So again, if you were to plot what is the force on the golf ball as a function of time from the golf club, you might get something that is some curve that sharply goes up and then comes back down over the span of a few microseconds. And even if you were privileged enough to know this force as a function of time, if what you ultimately want is acceleration, you could of course do that by Newton's second law. But this is just telling you what is the acceleration of the ball at every one of these little points in time over the span of a few microseconds To get the velocity as a function of time would then involve you having to do some integral over the acceleration, which then would involve you doing, over the mass, involve you doing an integral over the force of, this very complex looking, perhaps not nearly as nice as what I've drawn. You would have to do some sort of messy mathematical integral over the force over the span of those few microseconds in order to figure out what is the overall velocity of the object. And it could be done. But there are easier ways. To do this, I have to first make an apology in that I've been lying to you. And that what I told you was Newton's second law is not actually what Newton wrote down as what we now call Newton's second law. It is an example of it, but it is not actually what Newton wrote down. So we have been writing down something like this: that the net force on an object equals the mass of that object times the acceleration of that object. Written in terms of velocities, because again, what we're ultimately trying to do here is it'd be much better if I could think about things in terms of velocities rather than accelerations. But I know acceleration is the derivative of velocity, so I could always write it like this. Which is, again, just saying, how velocity changes with time is related to the net force and the mass. This also is not what Isaac Newton wrote down. And what we have been doing here, we've been making an assumption in all of the problems we've done to date that I've been kind of pushing under the rug, in that we have been assuming up to now the mass is always a constant. We have been assuming m is a constant. If the mass is a constant, what we wrote down for Newton's second law is perfectly correct. If the mass is not a constant and is changing with time, for example, like a rocket, it's shooting fuel out of the jet, the mass is changing with time. The way we wrote down Newton's second law would have actually given you the completely wrong answer. Now, how often are we going to assume the mass is actually changing? Rarely, if ever. So what you wrote down for Newton's second law is still perfectly appropriate. But let's utilize that fact here. And so let me write down Newton's law. So the sum of the forces equals the mass times the acceleration, or the change in velocity. Go backwards with the derivative. Remember that a constant pops out of the derivative. Now let's put it back in. So if the mass is a constant, then that is the same thing as this. If I erase this middle part and move this over, this is actually what Newton wrote down. This is the true version of Newton's second law. Which allows for things like the mass to change with time. In that case, the mass m would not just pop out of the integral, or pop out of the derivative. You would have to use the product rule, and that might be something like v times dm dt plus m times dv dt, which is not just F equals ma. But for us, what we're going to do here is this quantity was clearly identified as being very, very important. This mass times velocity. and we define that as the momentum of an object. It is a vector. So we're back to dealing with vectors. Momentum is a vector quantity. There is not only magnitude, but there is directionality that is associated with an object's momentum. So another way of writing Newton's second law is that the sum of the forces acting on the object is saying how momentum changes. This might be another way to write down Newton's second law. The sum of the forces acting on an object, we were saying equals mass times acceleration. Really what Newton said is that the sum of the forces acting on an object changed the object's momentum. How momentum changes with time, which again, that's just a way of saying the derivative. The derivative is saying how does this quantity change with time. Momentum changes with time when forces are applied to an object. If the mass is a constant, this just reduces down to sum of the forces equals the mass times the acceleration. But more generally, Newton's law is saying that forces change momentum. Now let's go back to the case of, well, I guess we could go back to the case of the wall with the ball, but I could just do this in general, because this is true in general. In general, we might want to ask, how does momentum change over long expanses of time? Again, Newton's law is a derivative expression. It's telling you at the instantaneous moment in time how momentum is changing. But I might want to figure out how is the momentum changing between t equals 0 and t equals 3 seconds, over a long span of time, not 1 picosecond, an instantaneous moment of time. So here we can just rearrange and do a little math with Newton's law. So let me take the case of for one force. F. So a force F is applied to an object. That makes the object's momentum change. I can always break the derivative up and think of it as a rise over run, so a little change in momentum in a given amount of small change in time. So I could write this as a little change in momentum is the result of a force times a little bit of change in time. So I'm just moving the delta t to the other side. Now I could say, let me take the integral of both sides of this expression. To get over long expanses of time, not just an instantaneous moment, but over long expanses of time, let me count up all those tiny little changes. Remember, an integral just is a fancy word for add up all the small little pieces. So I'm adding up all the small, tiny little changes in momentum. This left-hand side is just delta p, the overall bulk change, final minus initial of the momentum. And that is saying that that is equal to an integral of the force over some amount of time. I'm going to rewrite it over here. How does momentum change? Well, all you have to do is give me a force, and I'll integrate over time, and I will tell you the overall final minus initial change in the momentum of that object. Note that this is somewhat analogous to what we saw with energy. With energy, we said the change in kinetic energy was the result of an integral of a force over a distance. This is the dot product. Forces applied over a distance changed energy. Momentum we just wrote down is forces integrated over time. So I would say here, forces applied over time change momentum. And if you're not quite sure on what is the difference between the two, you are not alone. It has taken me years to gain an appreciation for why these are two very different quantities. Because you might think, okay, if I'm applying a force over a distance, like pushing an apple across a table, I am both doing work, and that's causing the object maybe to speed up, but I'm also applying that force, me pushing the apple, over time. It takes time, as the apple moves across, and I'm pushing as a function of time the apple across the table. And you're right. In that case, you are changing both the energy of the apple and the momentum of the apple. And obviously, they better agree with one another. If one says your speed is 10 and the other says your speed is 8, then something clearly is wrong with physics. But also appreciate that momentum and energy are also quite different things. Forces over distances is telling you how energy changes, which is a scalar quantity. It's not telling you anything about the direction. It's just telling you roughly how fast the object is moving, because it says something about kinetic energy. Momentum is also saying something about velocity, since momentum itself is just mass times velocity. But it's keeping everything as a vector quantity. It's saying something not only about the speed, the magnitude, but it's also saying something about the direction as well. It's saying something about why when the heavier mass object collides with the smaller mass object, that certain motion occurs versus some other setup, for example. So it is definitely true that interactions can change both at the same time. But again, not always. Again, the ball kind of bouncing off the table. I would say in that case, really, there's not a lot of work being done, right? The energy of the ball doesn't end up changing that much from start to end because no work is being done. The ball really isn't moving when it's colliding with the table, and then the table itself is not moving either. But there is still a large amount of momentum change because the direction of the velocity is flipping sign. Not to get too much into the weeds, but you might think, well, something has to be doing work, right? Because the velocity of the ball goes from some value to 0 and then to some non-zero value again. And you're right, and it's that deformation of the ball that is actually, there is actual force over a distance. There is things that are moving, that there is some amount of work being done in deforming the ball. That is why the kinetic energy can go down to 0 and then go back up to a non-zero value. All right, and to continue with this analogy, the integral of f over distance we called work, recall. The quantity f over time we call impulse. The name motivated, again, because a lot of utility comes out of the idea of looking at collisions, where the forces that are acting over time do occur over incredibly small amounts of time. Little, microseconds worth of time. So it is kind of like an instantaneous impulse on the system. Note here, impulse, also a vector quantity. Oh, I guess I should say, sometimes this is called J. All right, also a vector quantity has the same units as momentum, which I guess I never wrote down what those units are. So the units of momentum is then the unit of mass times the unit of velocity. This is not given any special unit name, so the unit is just kilogram meters per second in MKS units, rather. The impulse here, like how work said how kinetic energy was changing, impulse is saying how momentum changes. When forces are applied for over a given amount of time, that changes the momentum, which includes knowledge about both how fast the object is moving and about what direction the object is moving in. So I could actually go back to Newton's second law where we wrote down, this. Again, what this really is saying is if I move this over and I assume, right, if I have my delta t be large and not infinitesimal, that's essentially saying something like this. But notice that these are kind of very similar to one another. So sometimes you'll see the momentum impulse relationship, which is just saying that J equals delta P. If you have something called the work energy theorem, you might call this the momentum impulse. The impulse momentum theorem or something like that. Again, all this is really saying is that impulse is how momentum changes. Forces over time change momentum. Forces over distance change energy. Let's see, this is worth a highlight. Which I guess connects back to this. It's really saying the same thing, if you look at this expression. So if we want to be quantitative about this, I could first think of this graphically. Let's suppose, right, let's go back to the ball that's moving that's flying towards the wall. And now, since we're dealing with vectors again, we have to start being careful and we have to say something about which direction is positive. So let me assume to the right is positive. When the ball hits the wall, the wall begins pushing back extremely hard to the left. So in some negative direction. So it might have something that kind of looks like this, for example. Maybe this is the amount of force as a function of time exerted on, from the wall on the ball. It comes down to some large negative value, and then as the ball loses contact with the wall, it shrinks back down to 0. So that might be, what is the force as a function of time on the ball itself. We could ask, how does this connect to, say, the momentum of the ball as a function of time? I should have given a little bit more space here. Let me assume that it comes down and kind of starts there. So there's a definite starting point. That's this point of contact here, and then a point where it loses contact here. Because I'm going to draw some dotted lines down to my momentum plot. And now suppose I want to plot the momentum as a function of time, in this case. So what would that look like? Initially, prior to making contact with the wall, Maybe I'll do this in green. Prior to coming in contact with the wall, the object might have had some momentum that had some roughly constant horizontal momentum as it moved towards the wall. It then comes in contact with the wall and starts to feel an extremely large force pointing towards the left. So, again, thinking of Newton's laws, thinking about momentum, there is an impulse being applied to the ball, which is trying to push the ball to point in the same direction as that force. So as a result, the momentum of the object starts to slow down. Eventually reaches zero, where the ball is no longer moving to the right into the wall, and then the ball starts to actually, if it was compressed, it starts to move slightly in the direction towards the left or in the negative direction, and starts to move in some direction, and eventually loses contact with the wall, and then sails off at some possibly nearly constant horizontal momentum, or velocity rather. So you're seeing how the momentum changes in the lower plot, and it is a result of the force being applied over a function of time on the top plot. And if we wanted to connect these two plots, we could say that the reason that momentum changes is, again, because of impulse, which is f over dt. Geometrically, of course, we can think of that integral as the geometric area under the curve. So all that I've drawn in red, it would be some negative area since it's below zero. So as a result, the change in momentum is negative. It starts from going from some positive value, drops down to zero, and then continues into the negative direction, which in that case, again, is just saying the direction has changed. It's now moving to the left. Let's see, did I have something else for this? Yeah, let's do one of these, just to test our intuition. So here's an example. Maybe you have a case where which of the following would be the easiest way to push a stalled car off the road, i.e. get the car moving with the highest speed. Right, your car is stalled, you need to get off the road as fast as possible. You might want to get its velocity, as large as you can. Would it be the best case if one person pushed on the car for 10 seconds? Would it be easier if two people pushed on the car for about 10 seconds? And assume they're roughly equal in strength. Would it be easier if one person pushed on the car for 20 seconds? Or is either B or C both equally valid approaches? So the answer in this case is D, either B or C. You can think of this, again, how is velocity changing? We now can rewrite this to think of how is momentum changing. So it's mv final minus mv initial. Or if the mass of the car is not changing, we might write this as mv final minus v initial. You'll see that a lot if the mass does not change. Or we could just write this as m delta v. How momentum changes is a result of impulse, which is the result of force being applied over time. So if we assume that the force is roughly a constant, I could write this as, some force times some delta t. If the force is constant, you can come out of the integral. The integral of all the tiny little dt's is the total amount of time that it took. So in this case, one person pushing for 10 seconds would give you a certain amount of impulse, which would change the velocity by some fixed amount. There's some, we're essentially relating this to this. If that same person pushed, what were my cases? If that same one person pushed for twice as long, the force stays the same, F stays the same, but this delta t doubles. So there's twice as much impulse, twice as much change in delta V. Or 2 people can push for only 10 seconds, so then delta T is only 10 seconds, but now F has doubled. And mathematically, that gets you the same answer for the impulse, or in this case, the same amount of change for delta V for both of those cases. Some examples to kind of also draw from intuition. A ball falls in the air. I release a ball, it falls down. It clearly is gaining some sort of velocity. It is moving downward with some speed. What does impulse tell us about how the velocity is changing? So we get to ball, example, ball falling. In this case, if I define down as, I could define down as negative, I guess, since we're used to saying up is positive. If down is negative, then the force due to gravity is negative mg. Okay, we have to be careful. Energy, we can't get sloppy. Energy, we didn't have to deal with vectors. Now we have to be careful again. So I could ask, what is the change in momentum of the ball? Which again is just m delta v if the ball is not changing. That is equal to the integral of the force from gravity over some time delta t. How long it falls, for example, from getting from my top hand to my bottom hand. This is just negative mg, which is a constant, so I can take it out of the integral. Integral over dt. And so I can say, if I can rewrite it again, I might say m delta v equals negative mg, and then I could say this is just some delta t. The masses cancel, and you get what we would have seen in kinematics. Right, in the case of how the velocity is changing, we wrote down, we had a kinematics equation, I'll write over on the side. We had this v final equals v initial plus the acceleration times time, or some delta time, some change in time. So if I move the initial velocity to the other side, that's just saying the change in velocity equals acceleration times delta t, which in this case, the acceleration is negative g. We get the same result. As must be the case, else what are we doing? What about, think about what's going on with impulse of a ball rebounds off a table and bounces back into the air. In this case, the impulse from the table is clearly acting very strongly on the ball, such that as the ball falls down and hits the table, it is experiencing a force due to gravity. Of course, gravity is still pulling down on the ball. Gravity doesn't turn off. But it's also experiencing a quite large surface force or normal force from the table during that impulse, during that short collision. That is what allows the velocity of the ball to flip over and then shoot the ball back up into the air. If you were to measure, and you can do this too. Remember, the normal force or the surface force I like to think is the bathroom scale force. You obviously don't break your bathroom scale, but you could take a bathroom scale, and if it's sensitive enough, you could throw an object, a big rubber ball down on the scale, and you would see that during that collision, it reads a very large number, and then once the ball leaves, it's 0 again. What about, say, jumping off the ground? Maybe I stand up and I jump into the air. What's going on there? And it's the same idea. Just in that case, really, it involves Newton's third law as well. You're pushing down on the ground with a very large force. You bend down and then your muscles are now pushing down on the ground. So as a result of Newton's third law, the ground then also pushes up on you with a quite large force. Now you are trying to push down on the Earth. The Earth, as a result, doesn't really move. But the Earth then pushes back up on you, and you might be able to fly into the air in that case. Or jump into the air, rather. Then, of course, where you have to be careful and where things get dangerous is you jump into the air and then you return to the ground. A force is then exerted on your feet to bring you back to rest. You go from having a non-zero velocity to being back on the ground, not moving. A force has to change your velocity to make it zero. So as a result, there's a quite large force that acts on your feet. So you have to be careful the way you land. If you land at a weird angle, that could cause your ankle to rotate, and you risk breaking your ankle. Where am I in time? All right, good. Let me make one simplification and then do 2 examples. Remember how we talked about how, a ball bouncing off a wall, bouncing off a table, my hands smacking you across the face. There is some function there is some force as a function of time that could describe that collision. It would be some weirdly shaped function that would be completely different for, a ball bouncing off a wood table would have a different looking function than the same ball bouncing off a metal table. There are different properties of the material, how the ball reacts when in contact with that surface would be different for different materials or for different balls, or if the ball hit the wall at a slight angle. So we never will really know what this function looks like. But it still might be useful. It would be nice to know, for example, if I jump into the air and land on the ground, or if I jump from a given height, maybe I jump off higher and higher rungs of the ladder, at what point do I risk breaking my ankle? In order to say something about that, I need to know roughly how much force I'm feeling when I say jump off a ladder and hit the ground. I could ask, on average, how much force is the table exerting on this ball to make it then fly back up into the air? So what we do is we take this expression, and remember the impulse, how momentum changes, is the area under the curve. So I take this integral, I calculate the area under this weird shaped curve that then tells me how the momentum changes. But the function might be complicated, I might not know it in advance. Can I turn this into something where I do know some quantity? So what we could do is we can approximate the force as, rather than being this ridiculous looking function, we can approximate it as if it were a constant. So I could approximate this force as being some constant value between the point of contact and the point of break. And it has some value, I'll say F average. That it is a constant during that entire time. And you select. Actually, that makes it a little bit unclear how we actually use this. So I'm not going to say we select. The value of F average in this case is whatever value ensures that the area underneath that red rectangle is the same area underneath your weird shaped function. The value of F average is whatever makes, I guess I can write that down mathematically, whatever makes the integral of F average dt equal to the true answer, which is some complicated function over an integral of that complicated function over time. Which again, geometrically, these just mean area under the curve. So I'm saying that the area of the rectangle equals the area of this kind of weird shaped function. This, in a sense, is how you define an average velocity. So typically when we're talking about impulse, if we ever have to think about impulses, we will say instead that J, which is always f integrated over time, we will approximate this as a constant f average over time. But if f average is a constant, it can come out of the integral. So then this is the same thing as f average over dt, or f average multiplied by some big delta t. And I'll recopy the j here so I can highlight this. This is an approximation, but it's an incredibly useful one, and not a bad one either. You might think, you just spent a good chunk of lecture talking about how this is this weird, complicated function, and now you're just essentially throwing all of that away and saying, let's just pretend it's a rectangle. And I claim that's okay for collisions, because again, remember, this is happening over an incredibly, incredibly small amount of time. So the approximation that is actually just a constant over that tiny amount of time actually is a fairly good one. You know, yes, there is times where it's very low, it comes up to some big value and then comes back down. But that all occurs over a microsecond. Any error you make in approximating that as just a pure average constant function is actually quite small. So this, I would say, right, the caveat is that, you know, for I guess for interactions, we might say, right, where there's small amounts of time, you know, pass. This is a decent approximation. If this is occurring over long periods of time, you have to make sure it's valid to call the force an average force. Or maybe you want to calculate what is the overall average force. Maybe that's still useful. I don't know. So how is this helpful? Like, let's think. I had one that seemed really good. So chapter 9, number 28. In Taekwondo, a hand is slammed down onto a target at a speed of 13 meters per second and comes to stop during the 5 millisecond collision. Assume that during the impact the hand is independent of the arm and has a mass of 0.7 kilograms. What are the magnitudes of the impulse and the average force on the hand from the target? All right, so maybe, I don't know. Do you chop blocks of wood in Taekwondo? Right, so you have some hand that is slamming down onto a table or a target or a piece of wood. And it's saying that the hand has a mass of 0.7 kilograms. That's the hand. It initially starts with some velocity of 13 meters per second, and then it says it comes to rest. So let's assume it's 13 meters per second down, and then comes to rest eventually in some delta t of 0.005 seconds. Then it asks, what is the impulse and the average force on the hand from the target? So I slam my hand down on a table. My hand clearly comes to rest. Something had to make my hand stop moving. A force had to change the velocity of my hand. That force, of course, comes from the target or the piece of wood or wherever you're slamming your hand down into. So in this case, I'm asking for what is the impulse, which is generally defined as f over some function, some function f over time. But also remember the impulse-momentum relationship. Impulse is just how much your momentum has changed. So that is mass of the hand v final minus mass of the hand v initial. The final velocity of the hand is 0, so that is just mass of the hand v final. V initial. So now I have to be careful about my signs. If I say, let's say down is positive. So if down is positive, then that means the velocity of the hand is plus 13 meters per second in that case. This ends up being a number that is negative 10.5 kilograms meters per second. Negative means it points up because I said that down was positive. So since it's negative, remember this is a vector. We have to, the negative means something again. Negative means it's pointing in the negative direction, which I've defined as up, which makes sense. There's a large force I'm feeling pushing up on the hand, which is stopping my downward motion and making it 0. Then it says, what is the average force that is being exerted on the hand? So in that case, I can say, with an average force, while this is always true, I'll approximate this as an average value over some time t. So I can write this as F average times dt. So in that case, I can solve for F average and write this as 1 over delta t, my impulse. Or, said another way, 1 over delta t, my change in momentum. So we just calculate what that was, negative 10.5. I divide by 0.005. The average force that the hand feels is negative 2,100 newtons. For comparison, right, you could think, what is the weight of the hand? The mass times 9.8 meters per second, the weight that gravity is pulling down. In that case, that is only 6.86 newtons, for comparison. So the target, the table, the piece of wood, whatever it is exerting an extremely large force pointing upwards so that it can bring the hand from moving to rest in 5 milliseconds. All right, I'm a little bit over time, but I just had one more example, so I'll do this example rather than waiting till the next class. Suppose it's a nice summer day. We're outside. You're standing still, hanging out. I then take a water hose and spray water directly into your face. And the water comes at some horizontal velocity. Hits your face, and then essentially just dribbles straight down. So it hits your face horizontally, and then falls off your face vertically. For a hose, if 1.5 kilograms of water hit you each second, at 20 meters per second, what force do you feel from the hose or from the water? Or rather, what is the force on your face? So we could start by looking at the water. The water has some horizontal momentum coming in, but then it loses all of its horizontal momentum. So the delta P in the horizontal direction, the final momentum in the horizontal direction minus the initial momentum in the horizontal direction. it ends up with no horizontal momentum, so this is just negative the momentum in the horizontal direction. And let's make to the right positive in this case. So I would say then this is negative 1.5 kilograms times 20 meters per second, plus 20 meters per second. And that's some number. I guess it's 30. Negative 30 kilograms meters per second. That is how the water's momentum changes from going into your face and then stopping. And then gravity then pulls it vertically downward. But we're not thinking vertically, we're thinking of what's going on horizontally. I can also relate this impulse, or this change of momentum rather, to an impulse, which I will approximate as some F average times delta t. And so I can write that the F average on the water is the change of momentum on the water times this small delta t, which in this case I think we're just going to call it 1 second. So that is then, I'm dividing by 1, so that's negative 30 newtons. You might think negative, it points to the left. And that is the case. We're focusing on the water. You know, the water's momentum went from positive to 0. So that meant a force had to be pointing in the negative direction to stop it from moving towards, in the positive direction. So this is the average force exerted on the water from your face. So then I would say the force of the water on your face. So maybe I'll call this F face on water. So then the force of water on face, by Newton's third law, is just equal and opposite to the force of the face on the water. So what your face feels is a force of plus 30 newtons. Plus meaning you feel a force pushing you to the right, as would be expected if I was pointing the hose to the right. Alrighty. That is impulse and momentum. Next lecture, we start to think about how this quantity may or may not be conserved.